And we're rolling. Okay, here we go. Let's go back. This is mostly out of our books, Singer, Foster, and Schultz, Basic Math for Electricity and Electronics. And so you know what it's all based on. And I've slightly modified the presentation they gave me. We're going to talk about the atom, an atom's smallest amount of an element. We've talked about that a little bit, maybe broken down into smaller pieces, but they may not have any of the properties of the element. Okay, now with all materials is electrical in nature. That's a new thing, by the way. Volts, what are volts? An electron differential pressure is required to move electrons along a wire. This is called voltage. All right. And we use the symbol E, and we measure it in volts. Named after Count Alessandro Volta, an Italian physicist. And the symbol for voltage is E, not V. I'll fix that later. You know what? I'll fix that right now. How do you like that? That's okay with you guys. It's a slide that I missed. No, go back. That's not going to let me change. All right. Anyway, you know that it's E. We're going to move on. A Coulomb, what is a Coulomb? The practical unit of electroquality represents a certain number of electrons and is called a Coulomb. A Coulomb is, well, I think it's going to tell us, 6.25 times 10 to the 18th electrons, or 6.25 exa-electron. That's an engineering notation term, and we're going to learn engineering notation. Named after Charles de Coulomb, a French physicist. In his honor, the symbol for a Coulomb is a C. Coulomb, move this out of the way for the moment. Early investigators suspected that electric force diminished with distance as a gravitational as similarly to the gravitational pull. Not in the same way, but that it is similar in that the charges are weaker and weaker as the two charges are farther and farther apart. The dependence of the force between charged bodies upon both distance and the charge had already been discovered but not published in the early 1770s by Henry Cavendish of England. And then in 1785, the French physicist Charles Augustin de Coulomb published his first three reports of electricity and magnetism where he stated his laws. And his law is, a Coulomb's law is that the magnitude of the electrostatic force of interaction between 2-point charges is just, directly proportional to the scalar multiplication of the magnitudes of the charges and inversely proportional to the square of the distance between them, which is very similar to the formula for gravity. Electrical current, and we use the symbol I for the intensity of the current flow. The speed of flow is nearly equal to the speed of light in a way. And in other words, if I wrap a wire around the whole entire Earth, and I shove one more electron in one end, it's going to come out the other end almost immediately, right? Because it's a chain reaction. Electrons actually move relatively slowly, but the chain reaction between this one hitting that one hitting that one, down a wire is almost instantaneous, and it happens at about the speed of light. The speed of an individual electron is much slower than the effective pressure of one end of the wire is felt almost instantaneously on the other end, no matter how far away it is. It's measured, we calculate it as amperes. The symbol is I still. Once again, it's a Coulomb of electrons passing one point in 1 second, and that's an ampere, named for André Marie Ampere. Still, the symbol is A for amperes. An insulator is a material that prevents electrons from traveling through it easily. Non-metallic materials like glass, mica, porcelain, rubber, and textiles are good insulators. No material is a perfect insulator or a perfect conductor. Although in DC theory, I'm sure that you've already learned that a material that has one or two free electrons in its valence shell is a good conductor. Something that it has 7 or 8 is a relatively good insulator. But I want to talk about very quickly about electrical pressure affecting how much something is a resistor or semiconductor or a conductor. If you take a regular voltage of say 400, 500 volts, 600 volts, something like that, and put that pressure on a circuit that has, let's say, some rubber in it, okay? At that low voltage, rubber is a pretty good insulator. But kick that up to 5,000 volts or 15,000 volts, and that rubber becomes a semiconductor. It's conducting pretty well at 15,000 volts, okay? So you got to remember, something that's an insulator is relative. High voltage cable splices call rubber tape semiconductor tape, and they call silicone tape, which is very, very expensive, insulating tape. What do you think we call vinyl tape? The thing you call electrician's tape. What do we call that? It's a conductor. That's correct. Because all it's intended for those who don't know, electrician's tape is only to keep moisture out of the connection. It has nothing to do with its insulating properties because it's not a very good insulator. Can you name a better insulator than vinyl tape? Porcelain. Porcelain's a vastly better one. How about paper? Plain old paper is a vastly better insulator than rubber, even. Paper's a pretty good insulator. There are places where they use purified mineral oil and paper to insulate high voltage cables. Okay. So remember that those terms are still relative. A conductor is a material through which electrons may travel freely, easily, shall we say. Most metals are good conductors. An insulator is material that prevents electrons from traveling through it easily. That doesn't mean it won't travel, it's just not as easy if it were a conductor. So it's a relative term. Although when we have the quiz, oh, that's right, that's a different class. You don't have to identify the number of electrons. The ability of a material to resist the flow of electrons is called resistance. Pure resistance only occurs in purely resistive DC circuits. This is a study of DC electricity, so we can talk about pure resistance, but anytime we're talking about AC power, anytime we're talking about a coil, we're going to have something that is not going to happen at the same time as the voltage that is supplied. It'll be out of phase, meaning that it's not going to be pure resistance. But that's a whole different semester. Okay, it's measured in ohms, and it's named after George S. Ohm, a German physicist. The symbol for resistance, of course, is R, or the ohm symbol. R for when we don't know the resistance, a specified number of ohms if we do. All right, a little quick quiz on what we've just gone over. An atom, what particle possesses a positive charge? What's another name for electrical pressure? Differential pressure, by the way. Approximately how many electrons are contained in 1 Coulomb? How many amperes are flowing in a conductor? If 3 coulombs of electricity flow, 3 coulombs of electrons flow past a given point in a wire in 1 second. And what is the unit of resistance? Let's look at those questions again, and now we'll look at them with the answers. Protons. In an atom, what particle possesses a positive charge? A proton. Electrons have a negative charge. Neutrons, neutral charge. Neutrons, neutral. Nice and easy to remember. Okay, what's another name for electrical pressure? Differential electrical pressure, by the way, because it's like a French toilet where we have the water stored on the top. The water on the top is stored energy. It's not doing anything. It's very similar to voltage. It's got the potential to have some force. When we open the valve, we see some current flow, Just like in electricity, we see the current flow. If there's current flow, it's doing something. Okay? Approximately how many electrons are contained in 1 Coulomb? About 6.25 times 10 to the 18th. How many amperes of current are flowing in a conductor of 3 coulombs? Well, we think that's about 3 amps, don't we? Okay. And what's the unit of resistance? Silly question. Ohm. Symbol is the omega of the Greek. Now, an inline ammeter, there are two kinds of ammeters. I want you to realize that now. There's one called a Hall effect meter. Hall effect ammeter is a clamp-on ammeter. That is not what we're going to talk about here. Okay? We're going to talk about an inline meter, like the meter that's in your DMM, your Fluke 117, or your Simpson 260, which is an analog meter. They both have an inline ammeter. And to connect them, to measure current flow, we have to connect them in series. That means we have to break into the circuit. So if you're going to read current with an inline ammeter, you must break into the circuit to read the current. And it indicates how many amperes are passing through that meter. Here's a couple of quick, simple, childish diagrams. I apologize if you were offended about how simple these are, but I want you to realize that in an inline ammeter, you'll notice that all the current has to go through this meter right here. All the power is going out. Let's see if this is going to work. Power is going out to the bulb. It's going back through the meter back to the battery. So that, we would say, is in series. How can we identify a series circuit? There is only one path for the current to flow. Write that down. Series circuits only have one path for current to flow. Voltmeter. Voltmeter is similar to something exactly the opposite. It shows you the electrical differential pressure. All right? And you're going to connect it in parallel with the load. Wherever you would like to, if you, I'm getting excited. If you measure from point A to point A, or a wire where the power is going, let's go back a couple slides there. Let me go to the next one, actually. I'm now looking at how we read voltage. If this voltmeter right here is in parallel with the load, current can go through the voltmeter and it can go through the load. Is that correct? That's correct. Now, it reads the difference between the voltage coming in here and the voltage down here. It's the difference in voltage. It's the difference in voltage between point A and point B. And in this load, you'll notice that we only have one resistor. So all of the voltage will be dropped across that resistor because it's the only load. If we had two loads, the voltage would be divided between the two loads proportionally because we know a little bit about Ohm's law, but we're going to. And so we would be able to read different voltages on two different resistors. So again, here's my nice and simple drawing where I've got my voltage coming out of, or my power coming out of one line here and going to the load and going back to the battery. But I'm just connected in parallel here to the meter. So you can see that this thing is connected in parallel. Okay, so a quick summary of this is that we have voltmeters measure differential electrical pressure, should be placed in the circuit across the resistance, and is also across the voltmeter. An ammeter is inserted into the circuit, breaks into the circuit, and receives the full current of the circuit. So what if your meter cannot take the kind of current that's in the circuit? You might want to use a different meter. Or there's a thing called a shunt so that you can read a proportion of the current, but we'll talk about that later. Okay, an ohmmeter is really an ammeter whose dial has been marked to read the resistance of the ohms instead of the current in amps. But what they don't tell you here is that an ohmmeter creates its own voltage. It's got a battery supply, and so it's sending out a known voltage. And what it gets back, it can read the DC resistance of the load that's put on the meter. So you can put it on. Now, how do you have to hook up a ammeter? Break into the circuit? Okay. Now, you would think, no, you break into the circuit. It's not parallel. But, and here's your big warning, make sure that all of the circuit power is turned off if you're going to use your ohmmeter, because your ohmmeter is creating a circuit of its own where you're sending out power, you're getting power back, and if it's getting 120 volts instead of 9 volts, you're going to burn up a fuse at best and maybe a meter. And because of that, when you go to the second semester and you buy a meter, you're going to buy a really good one, but you're going to buy one that has 2 fuses, one for the current and one for the rest of the meter. And it is much better to burn up a fuse than a meter. Okay? Alrighty. So, an ohmmeter supplies its own power source. And I want you to realize that what people do with an ohmmeter looks like they're reading something in parallel. But what they're creating is a simple series circuit. If we know that this resistor right here is connected to some more circuit someplace else, as long as it's turned off and we only connect the meter here and here, we've created a series circuit through the meter, through the load, and back through the meter. Everybody see that? So it's actually a series circuit, isn't it? We've created our own little circuit, right? And it's a series circuit. You'll notice that if you have just a resistor all by itself, you can read it with this thing because it's going to send out voltage, send it through the load, and see what it gets back, and it figures out what the resistance is from what it gets back. Okay, now a wattmeter, where's my, okay, there we go. A wattmeter is really an ammeter and a voltmeter combined to see what apparent power it sees and indicate the true power. Watts is a measurement. Have we talked about true power and apparent power here? We have not, have we? Okay. Let me tell you, this is a good time to tell you this. Apparent power is whatever is coming in. When you get an Edison bill, it says watts, but it's a lie. They're charging you for every volt that comes in and every amp that flows in. That's called apparent power and is measured in volt amps. So if we're using 120 volts at 10 amps, how many VAs are we taking in? Somebody say 1,200. That would be incorrect. 1.2 kVA. 1.2 thousand K, K is 1,000. VA volt amps. 1.2 thousand volt amps. Yes, sir. Hold that question. So, what's coming in is what's called apparent power. Even though Edison calls it watts because they want to bill you for that, they think you're getting the full use out of that. Let's say that you're running a little pool pump, okay, and you're running it, and it's pulling 10 amps, and it's 110 volts, 120 volt pump, and it's pulling 10 amps. It's 1,200 VAs, right? But it says right on it that it's a 1,000-watt motor. What does that mean? That's not it's only cranking out 1,000 watts of output. It doesn't say watts on the motor, it says horsepower, right? What if that's a 1 horsepower motor? That means it's only creating 746 watts of cranking force. Let's say it's taking in 1,200 VAs. That's terrible efficiency, isn't it? Is that possible? Believe it or not, that's not even possible. That's fairly likely. 746 divided by 1,200 is 62% efficient. That's a little below the national average for code book motors. Code book capacity for a motor, most of the motors that the code book looked at way back when were very low efficient motors. They were like 70% motors. Well, motors have gotten a lot better than that, and because of that, well, we won't get into that. Motors have gotten more efficient than that, but I want to talk about wattmeters real quick, and I'm trying to explain that VAs are the incoming power. Watts is what the actual cranking force. And a wattmeter can actually only read the actual power being dissipated by the circuit. So if we put this wattmeter on that 110 volts, or 120 volts, 120 volts, that's pulling 10 amps for that motor, the voltage portion of the meter will be connected to the circuit in parallel to read the voltage and in series to read the current, right? So all that 10 amps is going to go through the wattmeter. So it's got to be a 10 amp or more rated wattmeter, or 1200 VAs or higher rated. So it's got to be a pretty good one. So it's going to read, is it going to read 1200? No, it's going to read 746 watts that motor is cranking out. Even though it's taking in 120 volts at 10 amps, which is 1200 VAs, that motor is actually only cranking 746 of cranking force, and that's under full load. That's its absolute maximum. Okay? Everybody see the difference?
So they charge you the difference on what's going
No, they do not. They charge you for whatever you're taking in, apparent power. So if you have a very inefficient refrigerator, for instance, which is one of your biggest loads, other than an air conditioner, of course, if it's inefficient, so sorry for you. You're still paying the apparent power. You're paying for apparent power, right? And that's why, if you go to Home Depot, you can find a thing called a green refrigerator receptacle adapter, and it plugs into your receptacle, and you plug your cord into it, and it makes your refrigerator slightly more efficient. And if you take my second semester class, I'll explain what's in that thing. And it's really cheesy. And they charge you 20 or 30 bucks for it. It's all of about 50 cents worth of parts. Maybe $1 or $2 at the very most. But that's way down the road. Okay, I just want to explain now the wattmeter is a device you may run into, and it's a handy thing because it will tell you the actual power that's going on. Okay, the Watt is named after James Watt. For those who don't know, I'm fairly fascinated with Watt because he was an inventor, and what he really did was he created an improved steam engine. And that doesn't sound like that big of a deal, right? But if you're trying to get people to buy your steam engine, you've got to get people to understand how they can use it, what it's doing. Now, everybody in the world was what kind of worker back then? A farmer. Everybody was farming. That was the only industry back then, right? Or one of the few, right? So he had to explain to these farmers why they wanted to buy his little improved steam engine rather than buying horses and feeding them. And so he decided he had to figure it out in terms they understood. So because of that, the unit of power is the horsepower, because he's trying to sell it to farmers. So he watched horses pull dirt up when they're plowing, and he figured they're pulling up about 220 pounds and moving it about a foot every hour. 220 foot-pounds an hour. That is a horsepower, for those who don't know. He also watched the mining horses, and he would watch them load the rocks. He would weigh them before they lifted, and then he'd see how fast they lifted it, and work being done, divided by the speed gives you the force, right? Okay, so he figured out, he's a pretty smart guy, right? I mean, he's operating back in what I would call basically the dark ages, okay? And he's smart enough that he figures out, hey, I gotta explain this to farmers because they need to understand this thing's making a lot more power than their horses. All right, so then he decides, well, electricity's happening, it's coming along. I've got to convert to that too. So I've got to figure out how much power that is. And so he figured out that it's about 746 of watts of electrical power is 1 horsepower. Okay. Electrical circuits. To have an electrical circuit, you have to have a complete path. What's wrong with the circuit over here on the right? You've got a battery, a light, and a switch. The switch is open, right? We got to close the switch to have a circuit? That's correct. We've got to have a complete path. Okay. And, okay, then we want to talk about a fuse. A fuse is to prevent large amounts of current flowing in a wire. So is a circuit breaker. And they're always connected in series, so all the current has to pass through the fuse or circuit breaker, so that when an excessive amount of current goes through it, it will trip. The circuit breakers in your panel at home are what are called either instant trip circuit breakers or inverse time circuit breakers. And now you're wondering, which one do I have at home? You have an inverse time circuit breaker. That means that if you have a 20 amp circuit breaker and it is pulling 20.02 amps, how long will it take to kick off? It probably will never kick off. Probably never. It's not that accurate. How about 22 amps? How long will it take to kick off at about 22 amps? It's about running about 10% over. About 3 hours. I know that's shocking to you, but it will allow that to happen, a 10% overload to happen for about 3 hours. I am not joking. Okay? Now, what happens when I go up? We're going inversely up, right? From 0.02 to 10%, right? 0.2% up to 10%, right? Okay, let's go much higher. Let's go 150%. So we're going up the exponential curve. At 150%, at 30 amps, how long will it take to kick off? A fairly short period of time. Okay? Now, let's go up even higher. We'll go up to 200% now, which is only a little higher on the exponential curve. Now it will kick off in about a quarter of a wave. In electrical energy, AC energy, it's created 60 cycles a second here in the United States. Okay? So 1/60th of a second is one wave. One. And 1/4 of that is 1/240th of a second. Is that correct? And that's how long it will take to kick off at 200%. That's known as inverse time. The higher the overload, the quicker it'll kick off. Because a short circuit will not create a 22 amp short. It'll create a 100 amp short, right? It will flow lots of current. Whatever the resistance back to the source is, that is going to be how much current flows. It's going to be in the hundreds of amps, not in the amps. So a circuit breaker is set to kick off when there's a big flow instantly in a quarter of a wave. But a little overbit, little tiny bit over its rated ampacity, it's going to let it go. Let it slide, baby. It's okay. All right? So that's how fuses and circuit breakers work. Especially, now we have instant trip. We have 4 things. We have instant trip circuit breakers and instant trip fuses. A little bit too much over, whatever its set point is, when it gets that amount over, it trips, period. With an inverse time breaker or a dual element time delay fuse, there's a time delay between the overage and when it kicks off. There's that inverse time thing that happens and fuses are generally used to start motors, so it lets a big overflow happen for a short period of time. But if that continues on, it will blow. That's why fuses are used to start motors almost all the time. Okay, so we know what a fuse is and a circuit breaker. Circuit diagrams. What do we have here? Every circuit diagram has got to have all these silly things. Okay. And let's have another little quiz. How must the ammeter be inserted in order to measure the flow of current in a wire? What does a voltmeter measure? That's a pretty silly question. When using an ohmmeter to measure resistance, should the power be on or off? Silly question. Must a complete circuit have to be a complete circuit? That's kind of a dumb question. What type of device is used to protect a circuit from excessive current? Okay, let's get those answers now. How must an ammeter be inserted? Directly into the circuit in series. Break into the circuit. We must break into the circuit. If you get a fill-in-the-blank question that says, how must an ammeter be filled in, you better have write down, break into the circuit. Break into the circuit. Break into the circuit. All right, that's enough of that. What does a voltmeter measure? Gee, I don't know, what does a voltmeter measure? Electrical pressure differential. An ohmmeter measures resistance. Do you think the power ought to be on? No, I think it ought to be on just to see the flames. I teach two classes where we use real AC power, and I really enjoy it when we blow stuff up. Okay, we all applaud, because the guy just probably burned all the wires that he bought. So, you ought to get at least a little applause. You know what I'm saying? Okay, what do you have to have a circuit? You have to have an unbroken path. And what type of device is used to protect? Oh, gee, I wonder, maybe a fuse or a circuit breaker? And believe it or not, that's the end of slide set number 1. And we just talked about, what did we just talk about? Somebody tell me. Is that all? Fundamental definitions, please. Fundamental definitions. Thank you.